Hey everyone, and welcome. Have you ever looked at a piece of code and wondered how developers figure out the absolute best way to solve a problem? Well, it isn't magic, and it's not just a gut feeling. It's actually a really systematic process called algorithm analysis. So today we're going to break down the fundamentals so you can learn how to grade any algorithm just like a pro.
So here's our game plan. We'll start by making sure we're all on the same page with our terms. Then we'll get into the criteria we use to actually judge efficiency. After that, we're going to get our hands dirty and analyze a simple algorithm for both time and space. And finally, we'll wrap it all up with the key takeaways. Sound good? Let's get started.
All right, first things first. Before we can analyze anything, we need to be crystal clear on what we're actually looking at. People throw around the words algorithm and program like they're the same thing. But in computer science, they are very, very different concepts.
I think the best way to think about this is to imagine building a house. The algorithm is your blueprint. It's the high-level plan, the logic, the sequence of steps you're going to take to solve a problem. You can write it in plain English, you can scribble it on a napkin. You don't have to worry about the strict rules of a programming language. A program, though, that's the actual house. It's built from that blueprint using specific materials. In our case, a specific language like Python or Java, and that comes with all the strict building codes, right? The syntax, the data types, declaring all your variables. The key thing is, we analyze the blueprint before you even start building.
Okay, so we have our blueprint. Now what? How do we know if it's a good blueprint? What actually makes one algorithm better than another? Well, that's where our efficiency report card comes into play.
This is really the heart of the whole matter. It's not just about, does it work? It's about how well does it work? And to answer that, we have to look at the resources it's going to consume.
For a long, long time, the two most important factors have always been time and space. First, how much time is it going to take to run? I mean, faster is almost always better, right? And second, how much memory or space will it need on a computer? An algorithm that's lean and doesn't hog memory is way more efficient. These two are our main grading criteria.
But what's really cool is seeing how this stuff evolves with technology. In today's world, especially with mobile devices, we care about a lot more. Like, how much data is it sending over the network? That's a huge deal for a snappy mobile app. Or how much battery power is it going to drain? That directly affects whether someone loves or hates your app. If you're doing really low-level stuff, you might even look at how many CPU registers it's using. But the classics, the fundamentals that apply almost everywhere, are still those big two: time and space.
All right, enough theory. Let's get practical. We are going to analyze our very first algorithm and figure out its time cost. We use a super simple, classic example just to see exactly how this whole process works.
And here it is. This is a simple little procedure to swap the values of two variables, A and B. You see, it uses a temporary variable called temp to hold on to one of the values so it doesn't get overwritten and lost. This is a really fundamental operation you see inside lots of other more complicated algorithms.
Okay, so the number one rule for a basic time analysis is to keep it simple. We make an assumption. Every simple statement, like assigning a value to a variable, takes 1 unit of time. Now sure, in the real world, a multiplication might take a few more nanoseconds than an addition, but for this high-level blueprint analysis, we just treat them all as one step. It lets us focus on the big picture. So that first line is 1 unit, the second line is 1 unit, and the third line is, you guessed it, 1 unit.
And if we just add those up, we get a total time cost of 3. Simple as that. Now, this isn't 3 seconds or 3 minutes. It's just 3 units. It represents a fixed, predictable amount of work that this algorithm has to do every single time.
So here's the most important takeaway. We're not using a stopwatch here. What we're actually doing is creating a function that describes the algorithm's performance. And the key insight for this one is that the time is always 3. It doesn't matter if A and B are small numbers or gigantic ones. It always takes exactly 3 steps to swap them. Because the execution time doesn't grow with the size of the input, we say it runs in constant time. In the world of computer science, you'll see this written in something called big O notation, as O of 1. Now, don't let that 1 confuse you. It doesn't mean 1 step. It's just a placeholder for any constant number, telling us that the performance is fixed.
Awesome. We've nailed down the time analysis. Now, let's take that exact same logic and apply it to our second big criterion: memory space. We're going to use the same little swap algorithm and see how much memory it needs.
Here we are again with our swap algorithm, but this time we're not counting the steps, we're counting the variables, because the variables are what hold information in memory.
And the rule for space analysis is just as simple. We assume that every variable we use takes up 1 unit of memory.
So we've got variable A, we've got variable B, and of course we have our little helper variable, temp. That's a total of 3 variables.
So the total space cost is 3 units. Now, you might be asking, why are we calling them words instead of, bytes or kilobytes? Well, that's because we're still at the blueprint stage. We don't know if these variables are going to be integers or decimals or something else entirely. So word is just a generic placeholder for 1 unit of memory space.
And just like we saw with time, the amount of memory this algorithm needs is totally fixed. It's always 3 words. It doesn't need more memory to swap bigger numbers. It just needs those same 3 containers. So we can say that its space complexity is also constant, or, you guessed it, O of 1.
And there we have it. We just successfully analyzed our very first algorithm for both time and space. So now let's just zoom out for a second to really understand the bigger picture and lock in what we've learned.
I absolutely love this analogy because it gets to the heart of how deep our analysis needs to be. Is this 1 unit per statement thing always enough? Well, for most of your day-to-day programming, yeah, it is. It's like knowing you just need to take the car to get across town. But what if you're writing the software for a rocket that's going to Mars, where every millisecond and every single byte of memory is absolutely critical? Well, then you can't just stop at constant. You have to know if that constant is 3 or if it's 3,000. That's when you have to do a much, much deeper analysis, all the way down to the machine code. The level of detail really just depends on the stakes of the problem you're trying to solve.
So here you go. This is your starter toolkit for analyzing algorithms. Just remember these key points. Count each simple statement for time and count each variable for space. And remember, the goal is to find a performance category like constant, not a literal time from a stopwatch. And finally, always keep in mind that how deep you need to go with your analysis depends on what you're building. With these simple rules, you are officially ready to start evaluating the efficiency of your own code. So the only question left is, what are you going to analyze first?